His special metal seems to remember its shape, but it is pure physics, not magic. It is called a shape memory alloy, defined by two distinct crystal structures. These phases are the soft Martensite state and the rigid austenite state. When cold, the metal is in the Martensite phase. Its internal atoms are messy. The low-temperature Martensite form is highly flexible and easy to deform permanently. Its messy crystal structure allows the atoms to slide easily under external force. Imagine the Martensite state as a relaxed, disorganized, but compliant student. The metal accepts the new temporary shape without any internal structural resistance. Even when bent, the atoms hold a faint memory of their original perfect arrangement. The key to recovery is adding energy to raise the temperature of the material. Heating the alloy provides the energy needed to trigger an internal structural shift. The messy crystals absorb the heat, forcing them to snap into an ordered pattern. This transition creates the austenite phase, where the atoms are symmetrical and strong. The metal's atoms are now perfectly organized, like a disciplined student focused on a task. The crystal blocks quickly rearrange and violently lock back into their precise positions. This structural reversion generates a powerful force, returning the metal to its programmed shape. The material actively pulls itself back to the original form with intense, concentrated force. The strength of this phase change allows the material to lift significant external loads. The wire can be twisted into any complex shape without creating permanent damage. A precise temperature input is all that is required to trigger the memory recall. The material instantly reverts from the temporary twist back to its original configuration. We utilize this reversible property in medicine and various complex engineering applications. In orthodontics, the wire gently and consistently guides teeth back into proper alignment. In surgery, tiny collapsed stents are inserted into blocked blood vessels when cold. The stent then uses the patient's body heat as the precise trigger to fully expand. Body temperature is the thermodynamic key, activating the shape recovery mechanism. The whole process is a repeatable, controllable phase transition between two crystal states. Martensite is the flexible, temporary shape that cooperates with the external force. Austenite is the high-energy, disciplined shape that dictates the true material memory. The material stores its memory purely in the design of its stable crystal structure. The shape recall is a physical property driven by atomic energy levels, not intelligence. The individual atoms aim to reach their most stable, low-energy configuration when heated. Without sufficient heat energy, the crystal structure remains frozen in its temporary form. A small temperature increase provides the energy needed for the atoms to swiftly rearrange. The structure dramatically locks into the original shape, confirming the phase transformation. A quick blast of heat or flame instantly undoes the complex manual twisting applied earlier. It is an incredible example of materials science utilizing structural physics brilliantly. The transformation cycle moves cleanly from cold to heat to its final hot programmed state. The material composition must be precisely balanced, like nickel and titanium in Nitinol. It is the metal that remembers its true form, a remarkable feat of smart materials engineering.